Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, a division of HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Present the conference. Bender's theory. Economics interpretation. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. In 1962 J.F. Benders published his theory oriented to optimization of large-scale problems. The fundamental idea is the partition of a problem into two sub-problems of reduced complexity based on the division of the variables like coordination variables and subordinate variables. The solution of the original problem is obtained by the coordinated solution of two complementary subproblems. The coordinator linked to the coordination variables, and the subproblem linked to subordinate variables. The subproblem provides information to the coordinator by the dual variables associated with its constraints. The coordinator takes the information from the primary level and incorporates it in the form of hyperplanes, Bender's cuts, limiting the feasibility region for the optimal solution of the coordination variables. Bender's cuts represent the cost of subordinate variables as a function of the coordination variables. The algorithm defined by Benders is convergent and solves the original problem through the solution of the coordinator problem, applies only to linear subproblems. Economic interpretation of Benders' theory. Some ideas on the interpretation of economics and Benders' partition and decomposition. From the economic point of view, large-scale methodologies allow to analyze systems from multiple points of view, both at micro and macro level. Holmerg, in 1996, in his paper Primal and Dual Decomposition as Organizational Design, Price and/or Resource Directive Decomposition, analyzes the relationships between mathematical structures encountered in optimization problems and the organizational structures, and it makes a parallel between organization charts and the flow of information and hierarchical algorithms, which give rise to different interpretations depending on the mathematical methodologies used. A coordinator problem resembles the functions of headquarters that interact with the coordinated subproblems that represent the subsidiaries, either by setting prices to use common resources, dual or price directive decomposition, like Lagrangian relaxation, or by fixing the level of activities common to all dependencies, primal or resource directive decomposition, like Bender's decomposition. The proposals made by the headquarters are analyzed by subsidiaries who generate new information, determining the level of activity in the first case, and specifying the marginal costs/benefits in the second. Based on the information obtained in the subsidiaries, the headquarters made a new proposal, fixing new prices or allocation new quantities. To solve the problem, a structure of two levels is established, based on the division of the variables of the monolith problem. Y are the coordinator variables, X the slaves variables. In the first level, is considered the equivalent problem in terms of Y, that is designated coordinator. In the second level, a problem for the variable X that generates extreme points for the coordinator problem. The solution is obtained exchanging information between the coordinator and the subproblem. The coordinator proposes values of Y and the subproblem generates extreme points or dual variables. Exist many interpretations of Bender's theory. For convenience, we assume that Bender's coordinator represents an authority, a manager, a system operator, a market operator, production vice president, that assign resources for many agents in a market or in a supply chain. Then, the first level defines the vector Y of resources assigned to the agents, sectors, factories, departments. The second level is a subproblem related with the agents that generates information about the resource's marginal productivity for each resource for each agent, or the prices that can pay the agents for the resources, represented by the dual variables. As reference, a typical list of cases, in which it is possible to apply partition and/or decomposition schemes. Investment planning. Usually problems oriented to determine investment plans have a structure in which the investment's variables control the operations variables. Many of investment's variables are binary, and the partition allows to handle two problems with different mathematical characteristics. The coordinator model, a mixed integer programming, MIP or MIMP, and the operations subproblem, a linear programming, or nonlinear programming, based on continuous variables. Multi-sectoral planning, optimizations models that link various sectors, it is possible to select as coordination variables transfers of goods, services, and resources between sectors, defining the production variables at the level of decomposition subproblems associated to each of the sectors. Multi-area or multi-region planning. When performing optimizations that integrate several areas, it is possible to select transfers of goods, services, and resources between areas as coordination variables, and define at the level of decomposition subproblems associated to operations in each of the area. As an example, an electrical system that interconnects several regions of generation and/or consumption. From the hierarchical standpoint, a sector may be composed of multiple areas. The concept of area may be illogical or physical, since also the area may be associated to regions, teams, market agents, etc. Multi-period planning, mathematical models that integrate multiple periods. It is possible to select transfers of goods, services, and resources between periods, variations of inventories or stocks, as coordination variables, and define at the level of subproblems the production in each period. Discrete time models always have this possibility. Stochastic optimization, an approach oriented to develop optimization processes that consider the possible scenarios of random variables that affect a system. It is normal to define a set of variables associated with the decisions to be taken regardless of the realizations of the stochastic process. This feature depends on variables associated to the simulated operation, conditioned on a possible scenario. Under this scheme, it is possible to define the coordination variables as those that are independent of the scenarios, and to define in the decomposition level, subproblems associated with each scenario. In this case, normally, all subproblems have the same matrix structure, allowing to design efficient algorithms for the joint solution of all the subproblems. In economics, the Cobb-Douglas, 1928, function is a production function, Q, widely used to represent the relationship between several final products and the use of technology inputs, T, labor, L, and capital, K. This type of aggregate modeling permits to estimate a country's production function, as well as the expected economic growth, that is, Q equals F, K, T, L. Two functions are essential in the decision-making process: the total cost, and the marginal cost. The cost of production is the result of integrating the marginal cost function from 0 up to Q. In the case of an industrial system, which produces a single product, the optimal production function can be constructed from the parametric analysis of an optimization model that minimizes production cost for different values of the quantity produced, Q. The solution of the problem fixes the optimal quantities of resource, T, L, K, to be used. When the model is solved using benders, the cutting planes represent the Cobb-Douglas function. During the processes, Bender's methodology generates marginal costs, or dual variables, cuts, approximated using a linear envelope based on an iteration cut plane. Then, in BT, the subproblem of the second level is associated to a linear production system. The set of Bender's cuts represents partially the total cost function. For a full representation would be necessary to know all the Bender's cutting planes. In this case, the main activity of decision makers will be to find the part of the total cost function that allows the best decision to be made, so that the decision maker has an intelligent oracle, the subproblem, to answer their questions about marginal costs. The figure presents the piecewise linear approximation of the fuel cost function, estimated in the article. A decomposition approach to the two-stage stochastic unit commitment problem. Published by Jung et al. In 2013. In markets, the clearing point, price and quantity, are analyzed to explain how various agents interact. The diagram shows the break-even point in a market under perfect conditions. A buyer's aggregate demand function is determined by the marginal cost curve. If you have multiple demand curves, the equilibrium will be determined by the equality of marginal costs, not by the quantities. The demand curve of a linear model will be a decreasing step curve. An example of a market coordination. Two large-scale methodologies allow systems to be analyzed, Bender's theory and Lagrangian relaxation. A coordinator problem resembles the functions of headquarters that interact with the coordinated subproblems that represent the subsystems. In Bender's decomposition, called Primal or Resource Directive Decomposition, the Bender's coordinator fixes the level of activities in all slave subproblems. Considering the coordinator's proposal, the agents make a price offer, or dual variables, which becomes an envelope of cutting planes. It is a primal method that works on feasibility and search of optimality. Lagrangian relaxation, or dual or price directive decomposition, is a dual of Bender's method. The Lagrangian coordinator fixes the level of prices in all slave subproblems. Considering the coordinator's proposal, the agents make quantity offers, or primal variables, which becomes an envelope of cutting planes. It is a method that works in unfeasible zone, or in optimality, searching the feasible zone. Dynamic coordination. Next, the dynamic evolution of Bender's theory is analyzed from the economic point of view. Consider a dynamic Bender's approach, in which the system is divided into periods. The problem must focus on how the information that is being produced dynamically can be shared. An alternative is to use an optimization knowledge expert system that dynamically connects the models. The optimization knowledge expert system store the information corresponding to the Cobb-Douglas functions, which are represented by Bender's cuts. The cutting planes can be stored in the expert system to be used in a new run, which is how it happens in the Bender's algorithm. The information of the cuts k+1, primal and dual variables, that represent Bender's and Lagrangian cutting planes, should be stored in the expert system. As it can be used later in k+2 period, this is because the exogenous sets and parameters change with each period. However, cutting planes can be used in every new period. In this way, Cobb-Douglas function information can be used at any time. An example of Bender's manual coordination. Below is the analysis that would make a professional trained to make decisions without mathematical models and the Bender's theory. Let's imagine a company that controls 3 plants, an industrial plant, an oil refinery, and an electricity generation hydro plant. The electricity generator has a capacity of 100 megawatt-hour. The company is managed by the CEO, who must make decisions about how to distribute electricity among industrial plants. The CEO assumes that each plant manager knows the demand function of his industrial plant, or knows how to calculate points from the plant situation. With this information, the CEO will surely solve the problem. The CEO has decided to coordinate the allocation of quantities for industrial plants, following Bender's approach. Plant managers must provide the marginal costs of what they have done with the amounts allocated by the CEO. This task can be done with a mathematical method such as Bender's, or by using his logic and moving any value in the direction that identifies the marginal benefit. If the CEO uses his computational knowledge, he could employ a Bender's model to solve the problem. If the company can't implement Bender's model, the CEO can use Bender's logic to do it manually. The steps to follow are: the CEO allocates an arbitrary number of gigawatt-hours to start the process. Plant managers should consider what they would do with the allocated quantities. Following the CEO's instructions, plant managers must report a willingness to pay for an additional amount of energy. To start the process, the CEO assigns 50 megawatt-hours as a starting point to each plant. This initial value does not need justification. To close the first iteration, plant managers answer $105/MWH for the industrial plant, and $90/MWH for the refinery. With this information, the CEO already knows that he must increase the energy allocation at the oil refinery and decrease that of the industrial plant. The marginal value, in this case the company's revenue, suggests to the CEO that he should increase the MWH allocated to the plant that generates the least marginal profit. If the marginal benefits are equal, an equilibrium solution is obtained, and the allocated quantities produce no benefit when exchanged. With the information obtained, the CEO knows that he must close a difference of $15/MWH in marginal benefit. With the information obtained, the CEO knows that he must close a difference of $15/MWH in marginal benefit. The new gap is equal to 0. The graph shows the trajectory of the process followed to reach the equilibrium of marginal benefits, and therefore the solution of the problem. Albert Einstein thought that imagination is the highest form of research. Thank you for your attention.